more than 6,000 light-years from the surface of the Earth, a rapidly spinning neutron star called the Black Widow pulsar blasts its companion brown dwarf star with radiation as the two orbit each other every 9 hours. Standing on our own planet, you might think you're just an observer of this violent ballet, but in fact, both stars are pulling you towards them, and you're pulling back, connected across trillions of kilometers by gravity. Gravity is the attractive force between two objects with mass, any two objects with mass, which means that every object in the universe attracts every other object. Every star, black hole, human being, smartphone, and atom are all constantly pulling on each other. So why don't we feel pulled in billions of different directions? 2 reasons: mass and distance. The original equation describing the gravitational force between two objects was written by Isaac Newton in 1687. Scientists' understanding of gravity has evolved since then, but Newton's law of universal gravitation is still a good approximation in most situations. It goes like this: the gravitational force between two objects is equal to the mass of one times the mass of the other, multiplied by a very small number called the gravitational constant, and divided by the distance between them squared. If you doubled the mass of one of the objects, the force between them would double too. If the distance between them doubled, the force would be 1/4 as strong. The gravitational force between you and the Earth pulls you towards its center, a force you experience as your weight. Let's say this force is about 800 newtons when you're standing at sea level. If you traveled to the Dead Sea, the force would increase by a tiny fraction of a percent. And if you climbed to the top of Mount Everest, the force would decrease, but again by a minuscule amount. Traveling higher would make a bigger dent in gravity's influence, but you won't escape it. Gravity is generated by variations in the curvature of space-time, the 3 dimensions of space plus time, which bend around any object that has mass. Gravity from Earth reaches the International Space Station 400 kilometers above the Earth with almost its original intensity. If the space station was stationary on top of a giant column, you'd still experience 90% of the gravitational force there that you do on the ground. Astronauts just experience weightlessness because the space station is constantly falling towards Earth. Fortunately, it's orbiting the planet fast enough that it never hits the ground. By the time you made it to the surface of the Moon, around 400,000 kilometers away, Earth's gravitational pull would be less than 0.03% of what you feel on Earth. The only gravity you'd be aware of would be the Moon's, which is about 1/6 as strong as the Earth's. Travel farther still, and Earth's gravitational pull on you will continue to decrease, but never drop to 0. Even safely tethered to the Earth, we're subject to the faint tug of distant celestial bodies and nearby earthly ones. The sun exerts a force of about 1/2 Newton on you. If you're a few meters away from a smartphone, you'll experience a mutual force of a few piconewtons. That's about the same as the gravitational pull between you and the Andromeda Galaxy, which is 2.5 million light-years away, but about 1 trillion times as massive as the sun. But when it comes to escaping gravity, there's a loophole. If all the mass around us is pulling on us all the time, how would Earth's gravity change if you tunneled deep below the surface, assuming you could do so without being cooked or crushed? If you hollowed out the center of a perfectly spherical Earth, which it isn't, but let's just say it were, you'd experience an identical pull from all sides, and you'd be suspended, weightless, only encountering the tiny pulls from other celestial bodies. So you could escape the Earth's gravity in such a thought experiment, but only by heading straight into it. Keep flexing your physics muscles with this TED-Ed series in which 2 CERN scientists simplify spacetime in 3 short videos.